So today we're getting ready for your test that you're taking through Zoom on Thursday, either in the morning at 8 a.m. or 6 p.m. In the evening. So looking at the following problem in front of us, we have tangent of tangent inverse of 5, 6. So remember when we were looking at tangent and tangent inverse, they're inverse functions of one another. And so they pretty much undo themselves. And so this is the same thing as what we have as our argument here, 5, 6. We need to be careful. Let's say we had something like tangent of actually it wouldn't look like that. It would be more tangent inverse of tangent of, let's say, 5 pi 6. Well, tangent inverse, our input has to be between negative pi halves and pi halves, and 5 pi 6 doesn't fall there. 5 pi 6 falls in that second quadrant. And so in this case, we can't just undo itself. We would have to look at this tangent of 5 pi 6. And so evaluating that, and show your work on your exam. So showing your work, I can give you some partial credit. So at least here, we could graph our angle of 5 pi 6. And so graphing that, we get here. So I'm technically evaluating tangent with my reference angle. And my reference angle I can find by looking at pi minus 5 pi 6. So 6 pi 6, which is pi, minus 5 pi 6 is pi 6. So our reference angle in here is pi 6. I know that tangent in the second quadrant, this is where we decide if it's positive or negative. Well, tangent in that second quadrant is a negative value. And so tangent of that 5 pi 6, it's equal to negative of tangent of pi 6. And so negative tangent of pi 6, which is 30 degrees is pi 6, is the root 3, negative root 3 over 3. Now we're thinking of tangent inverse, and tangent inverse, we had to limit that domain of tangent in order for it to be 1-to-1. And so we looked at values between negative pi halves and pi halves. And so I know that within those two quadrants, negative pi halves and pi halves, tangent is negative in quadrant 4. And so we're going to think about the reference angle that would give us root 3 over 3, which was the one that we used over here, pi 6. But this time we're just looking at it in our second quadrant. And so to get pi 6 here, we would look at 2 pi minus pi 6, or 12 pi 6 minus pi 6, which is 11 pi 6. So actually, it is 11 pi 6, but that does not fall between negative pi halves and pi halves. So it's even easier than that. We will just write this as negative pi 6. Okay, so let's look at another one where maybe we didn't know the value and it didn't fall out like that. So let's say you had tangent of cosine of 5/7. And let's say this is cosine inverse in here. So we don't know what value of cosine would give us back 5/7. And so if we don't know what that value is, then we're going to want to create a triangle. So we're going to do some substitution here. We're going to choose our value of A, angle A, to equal cosine inverse of 5/7. So we want to undo that cosine inverse, and you can do that by taking the cosine of both sides of our equation. So if we take the cosine of both sides of our equation, we get cosine of A is equal to cosine of that cosine inverse of 5/7. whole point of that was so that would fall out and give us just 5/7, the argument. And so now let's create our triangle. So thinking of cosine as the ratio of sides of a right triangle, we know cosine is adjacent over hypotenuse. And so adjacent side is 5. Let's call this angle A. So adjacent from A is, in this case, 5, and hypotenuse is 7. And so we need to figure out what the opposite side is. Maybe let's just call it y here. And so y is equal to, using that Pythagorean theorem, we're looking at c squared, the square root of c squared, minus 5 squared. So I just did that because we've been doing this so much, 49 minus 25, that I didn't write it out. So this is 49 minus 25, which is 14. No, it's 24. So some of you on your end of the chapter 7 test, or maybe even on this test, you might have gotten your answer wrong, but it was actually correct. You didn't reduce what was underneath that radical. So if for some reason you were taking that test or any end of the chapter test and you were marked wrong, but you had the right concepts, come and meet with me during student hours or set up a time with me. We can go over your exam together and I can give you partial credit on those. When you take a test in my class through the Zoom, you guys are gonna come in, have your webcams on, directed towards you. Sometimes students, if they don't have a web camera, if you're here in Yuba City or Marysville, you can come in and get a webcam through the school. But if not, some students will have their phone on while they're also, and their camera on them, while they're also on the computer. But anyways, so I kind of got sidetracked. But the whole point was for you want to reduce this. Also, when you're taking the test through Zoom, I will be grading it more extensively and I'll look at it and give you partial credit. So again, most of you show your work where you can. And if you didn't get it right, I can give you partial credit. So simplifying this radical here, this is the same thing as y is equal to. So 24 is 4 times 6. 4 is a factor of 24, which is a perfect square. So we can pull that out and y is equal to 2 root 6. Okay, so we found the opposite side of A. And so let's go back in and rewrite our expression. It's tangent of cosine inverse of 5/7, but cosine inverse of 5/7 we chose to be A. So now if we look at our triangle, we know that tangent is opposite over adjacent. So opposite side, which we just found, was 2 root 6, all over the adjacent side, which is 5. So when you're dealing with the composition of functions and you are looking at an inverse function where you don't know what angle would give you back that argument, then create your triangle. Okay, so in front of us is a problem from an old exam that I've given, and it tells you that tells you basically how much each thing is worth. But it wants us to evaluate the following. So sine inverse, so it's having, and the expression has the inverse function in it, so we have to think about limiting our domain. Our domain is between, or our output, I'm sorry, is between negative pi halves and pi halves. So I have sine inverse of root 2 over 2. So I notice that it's positive, so it's falling between 0 and pi halves. And so thinking to yourself, what of sine would give me back root 2 over 2, which is in quadrant 1. and that is pi fourths. So the next one, we have cosine inverse of negative root 3 over 2. And so again, we're thinking backwards. Cosine, though, is between 0 and pi. So think about your angle. Is it positive or negative? And that will tell you what quadrant you're thinking of. Since it's negative, I'm going to be in quadrant 2 between pi halves and pi. So I kind of ignore the negative and I think to myself, cosine of what is root 3 over 2? And that's cosine of 30 degrees or pi 6. And so this would equal, but it's pi 6, which is in the quadrant 2, that pi 6 is my reference angle. And so I can figure out what angle gets me there by looking at pi minus pi 6. So that would give me 5 pi 6. Then we have sine inverse of negative 1/2. So I have a negative value. Sine is between negative pi halves and pi halves. And so since I have a negative value, I know I'm in quadrant 4. I think about the positive. Sine of what gives me back positive 1/2, which is 30 degrees or pi 6. And so getting that down into the fourth quadrant between negative pi halves and pi halves, this would be negative pi 6. So this next problem, tangent inverse of tangent of 5 pi 4ths. So normally the inverse function and its original function will undo each other, giving us the argument. But we need to be careful because we have that inverse in the expression, and tangent is only between negative pi halves and pi halves. And 5 pi halves does not fall in there. 5 pi 4ths, I mean. So 5 pi 4ths, tangent of 5 pi 4ths. So let's graph where that is. Well, 5 divided by 4, that's bigger than 1. So I'm going to go past getting into the third quadrant and adding another pi 4ths to the 4 pi 4ths. That gives me a reference angle of pi 4ths. And I'm in quadrant 3. Tangent's positive in quadrant 3. And so I think to myself, what is tangent of pi 4ths? And tangent of pi 4ths is 1. And it's 1 in quadrant 3. And so now when we evaluate this tangent inverse of 1, we're looking at, again, the output, it has to be between negative pi halves and pi halves. And so tangent of what gives me back 1? Well, tangent of pi 4ths gives me back 1. And so this is equal to pi 4ths. So part E, we have sine inverse of cosine of negative 7 pi 6. So let's look at cosine of negative 7 pi 6 and evaluate that, working our way out. And so cosine of negative 7 pi 6. So let's graph negative 7 pi 6. Well, 6 goes into 7 once, so we're going to be going past the pi mark and then adding pi 6 to pi will give us 7 pi 6. And we went clockwise because our angle was negative. And so thinking about our reference angle, the reference angle in here is pi 6. Cosine, though, in this quadrant 2 is negative. And so thinking about sine inverse of, thinking about the sine inverse yet, but thinking about cosine of pi 6, I know cosine of pi 6 is root 3 over 2, but again, we're in the second quadrant, so that's negative. So when we evaluate sine inverse of negative root 3 over 2, we are between negative pi halves and pi halves because we're dealing with sine inverse. And then we're thinking to ourselves, sine of what first gives us back root 3 over 2, which is 60 degrees or pi thirds. but this is negative, so we want it to fall into the fourth quadrant and be written as radian measure between negative pi halves and pi halves. So that's going to give us negative pi thirds. So the next one, cosine inverse is sine of 7 pi 6. Well, again, working our way outwards. So sine is 7 pi 6. So graphing that 7 pi 6, that's going to get me down into the third quadrant. It makes me have a reference angle here of pi 6. And so sine of pi 6, that is 1/2, but we're in quadrant 3, so sine is negative in quadrant 3. So this is cosine of negative 1/2. And that's not cosine, it's cosine inverse. And so again, I would think cosine of what is positive 1/2? Well, cosine of 60 degrees, which is pi thirds, is positive 1/2. I'm using cosines, so we're going to be between 0 and pi. And so I need to figure out what that angle is. And I know my reference angle is pi 6. Actually, oh yeah. No, my reference angle is not pi 6. It's 60 degrees is pi thirds. But the angle that gets me there is 2 pi thirds. So this is equal to 2 pi thirds. Okay, so in front of us, it says solve the following equations, and we want our solutions between 0 and 2 pi. So looking at the first equation in here, you have cosine, 4 cosine squared minus of theta minus 3 equals 0. And so when we're dealing with this, I only have one trigonometric function in there, which is good, but there's only one term with that trigonometric function. And so I see that I can solve this by using the square root method. So I want to isolate my cosine squared theta. And I can do that by first adding 3 to both sides of my equation. So doing that, I get 4 cosine squared theta is equal to positive 3. Now I can get rid of the 4 in front of the cosine squared theta by dividing both sides by 4. And if we do that, we get cosine squared theta is equal to 3/4. So in here, I have cosine squared theta, and I want cosine theta. And so in order to get cosine theta, I can use the square root method and take the square root of both sides of my equation. So I get the square root of cosine squared theta is equal to plus or minus the square root of 3/4. So cosine theta is equal to plus or minus the square root of 3 all over the square root of 4, which is 2. So I'm looking at all values of theta. That would give me cosine of that value, positive or negative root 3/2. So I think for myself, what value of theta in the first quadrant would give me back positive root 3/2 for cosine. And that is at 30 degrees or pi 6. And so it's plus or minus in here. And so I have to think, in this case, I have to think of all 4 quadrants because we didn't have an equation with cosine inverse. It started with cosine. And so I would think about all 4 quadrants, cosine of the value that either gave me back positive root 3/2 or negative root 3/2. So first quadrant, like we said, was pi 6. So in the second quadrant, I would have pi minus pi 6, which is 5 pi 6. To get into the third quadrant with a reference angle pi 6, I'd add pi to pi 6, which is 7 pi 6. In the second quadrant, my reference angle is pi 6, so subtracting that from 2 pi, that is 11 pi 6. So in here, for all of the values between 0 and 2 pi, that would give me, or solve that equation, would be these 4 angles. If it had asked me for all solutions, then for each one of those angles, I would add plus 2 pi times k, where k is an integer. Because that we would do full rotations, and that would give us back to the terminal side. That gave us that value. So our next problem in front of us is sine of 2 theta minus pi halves equals -1. So since our argument here is not just theta, let's just do some substitution for a minute. So let's call a 2 theta minus pi halves. And so rewriting this, let's look at when is sine of a equal to -1. So I don't have the inverse function, so I'm thinking about anywhere between 0 and 2 pi where sine would give me back -1. Well, sine gives me back -1. Sine is the y value of the point on the unit circle. And so this is where we would hit -1 for y, and that is 3 pi halves. So I know my value of a that would give me back -1 for sine is 3 pi halves. But a was 2 theta minus pi halves. So we want to look at when is 2 theta minus pi halves equals 3 pi halves. And we have to add on here this plus 2 pi k. And the reason why we do that is, remember when we were graphing these functions, when our argument wasn't just theta, we had some shifts going along there. So we have to compensate for that. And so we can do that by adding that plus 2 pi k. So we're trying to figure out what theta is, and we can do that now by solving for theta. So solving for theta here, we would add plus pi halves to both sides of our equation. And we get 2 theta is equal to 3 pi halves plus pi halves is 4 pi halves. And 4 pi halves is just 2 pi plus 2 pi k. So getting theta by itself, let's divide everything through by 2. And so we're looking at theta is equal to pi plus pi k. So if we wanted all solutions, we would stop there. But we want all solutions between 0 and 2 pi, including 0 and not 2 pi. And so this is where you start plugging in values for k. So, and we stop once we find where we're getting outside of that input between 0 and 2 pi. So let's let k equal 0. If we let k equal 0, notice we'll get pi plus pi times 0 is 0. So we get theta is equal to pi. If we let k equal 1, we have pi plus pi times 1 is pi. So pi plus pi is 2 pi. 2 pi does not fall in this interval because of the inequality doesn't have the equal to part on it. And so this would be theta equals 2 pi, but that's not in our interval, so we wouldn't look at this. So anything bigger than 1 for that integer is going to get us outside of that interval. But I also notice, and sometimes the negatives work, if we put in -1 for k here, that's negative pi. A negative pi plus pi is 0. And so theta equals 0 does fall between this 0 and 2 pi. The 0 is included. So we have 2 solutions here that would give us that -1 for theta if we plug it in. So the next equations in front of us, I noticed that both of them have sine and cosine. So if that's the case, we want to manipulate the equation so it has just one trigonometric function. And so we can do that by using some of our identities. And one of our identities is that Pythagorean identity that cosine squared plus sine squared equals 1. Cosine squared theta. I should say that the angle in there. Sine squared theta is equal to 1. And so I notice here I have a cosine squared theta and a cosine theta. So I want to manipulate that sine squared theta to be in terms of cosine. And so I can do that by using this identity. I can subtract cosine squared theta on both sides. And so we get sine squared theta. We can rewrite this as 1 minus cosine squared theta. Okay, so rewriting that sine squared theta is the same thing as 1 minus cosine squared theta minus this cosine squared theta is equal to 1 plus cosine theta. I notice that this is a quadratic, and so quadratic equations, we want to get everything to one side of the equation a lot of times to solve that and then factor. And so before I do that, let's combine like terms on the left-hand side. And so notice you have a negative cosine squared theta minus a cosine squared theta. So that's going to give us 1 minus 2 cosine squared theta is equal to 1 plus cosine theta. So setting this equal to 0, I can subtract 1 on both sides of my equation. And at the same time, let's add 2 cosine squared theta. So we get 0 is equal to, or I'm going to put the 0 on the right. 1 minus 1 cancels out. And then we have 2 cosine squared theta plus cosine theta. Those aren't like terms because one is squared and one is not. Is equal to 0. So factor. Notice that they both terms have 1 cosine theta in common, so we can factor 1 out, and that would give us cosine theta all times 2 cosine theta plus 1. Equals 0. And so now that it's factored and set equal to 0, we can set each factor equal to 0 and solve if needed. So we have cosine theta equals 0 and 2 cosine theta plus 1 equals 0. So for this first equation, cosine theta equals 0, cosine theta is equal to 0 at pi halves. And just looking at values between 0 and 2 pi, not including 2 pi, but including 0. Cosine theta is equal to 0 at pi halves and 3 pi halves. And so now looking at the next equation, 2 cosine theta plus 1 equals 0. We want to solve and isolate cosine theta. We could subtract 1 on both sides. We get 2 cosine theta equals negative 1. Divide by 2, we get cosine theta equals negative 1/2. And so values that give me negative 1/2, those would be when my reference angle falls in the second and third quadrant for cosine. My reference angle would be 60 degrees, which is pi thirds. So in the second quadrant, reference angle pi thirds, pi minus pi thirds is 2 pi thirds. So theta equals 2 pi thirds. And it's also reference angle pi thirds, and that's not right. Not to scale, pi thirds would be more up here. Reference angle pi thirds in that third quadrant. So pi plus pi thirds That's 4 pi thirds. So we didn't have to add that plus 2 pi k like we had done in the previous problem, because our argument when we started was just theta. Where here, our argument when we started was not just theta. And so if that's the case, if it's not just theta, again, you want to add that plus 2 pi k in there. I guess we would actually add that plus 2 pi k if this said all solutions. But we have to be careful and add that plus 2 pi k and choose values for k when that argument wasn't just theta. Okay, so looking at that last problem. We have 4 plus sine theta is equal to cosine squared theta. So again, I see that we have both sine and cosine in here. Because of my identity has cosine squared and sine squared, let's, in this case, rewrite cosine squared in terms of sine squared. So using this Pythagorean identity, getting cosine squared by itself, we see that cosine squared theta is equal to 1 minus sine squared theta. So rewriting this, and as we rewrite it, let's distribute that 4 inside the parentheses. And so distributing that 4, we get 4 plus 4 sine theta is equal to cosine squared theta, which we just saw was the same thing as 1 minus sine squared theta. So this is quadratic, get everything to one side of the equation. So we could do that by subtracting 1 on both sides of our equation and adding sine squared theta to both sides of our equation. So in doing that, we get sine squared theta plus 4 sine theta. 4 minus 1 is 3, so plus 3 equals 0. So notice this is factorable. My value coefficient in front of my square term is 1. And so, and the two numbers that multiply to give me 3 and add to give me 4 would be 3 and 1. So this is plus 3 and plus 1. So sine theta plus 3, that quantity times the quantity sine theta plus 1 is equal to 0. So set each factor equal to 0. We're looking at when is sine theta equal? Well, sine plus 3 equals 0. Sine theta plus 3 equals 0. And when is sine theta plus 1 equals 0? Well, this is when sine theta equals negative 3. Okay, that's a problem. This argument is 1, or we don't have any stretching of that graph. There's no output that gives us back negative 3. We're following our ranges between negative 1 and 1. And so there's no value of theta that would work there. And so this one is not possible. If you tried to look at sine inverse of negative 3 on the calculator, it would come back that there was an error. So over here, sine theta plus 1, isolating sine theta, we get sine theta equals negative 1. So there is a value of theta that would give us back negative 1, and that was 3 pi halves. And we're only looking at values again between 0 and 2 pi. This would be the only one that would work. So looking at proving the following identity, we have sine squared theta all times 1 plus cotangent squared theta equals 1. So I see here that this 1 plus cotangent squared theta may, or we could manipulate it to use it, look like one of our identities. So going back, and I'm not sure if maybe that wouldn't be the best way to approach that. Instead, let's rewrite cotangent squared theta in terms of sine and cosine. And so if we did that, we would have sine squared theta all times 1 plus cotangent squared theta. Well, cotangent, that could be rewritten as cosine squared theta all over sine squared theta is equal to 1. So distributing our sine squared theta, I noticed that that fraction is going to go away. So sine squared theta times 1 is sine squared theta, plus sine squared theta times cosine squared theta over sine squared theta. Same sine squared thetas cancel, leaving you with cosine squared theta. And recall, when we're showing identities, we're only working on one side. So working with our left-hand side. And so working with that left-hand side, notice what we got, sine squared theta plus cosine squared theta, and that is that one identity, and that is equal to 1. And so we showed that one side gives us what we want, and so we proved that identity. So you guys should be able to graph your trigonometric functions. You should be able to figure out what the amplitude is if the function has an amplitude. Only sine theta and cosine theta have amplitude. You should be able to figure out the period of your graph. You should be able to figure out the range, and you should be able to graph at least one period. And so looking at the following, we have f of x is equal to -2 sine pi x minus 1. So looking at what's going on here, I notice my argument is not just x, it's pi x. And so that's going to affect my graph, and it's going to affect the period. And so what I really like to do is take my argument and sandwich it in between what one normal cycle would be. And usually we graph between 0 and 2 pi for one cycle for sine. And so let's sandwich this pi times x in between 0 and 2 pi. And so solving for x in this inequality, compound inequality, would divide everything through by pi. So doing that, we get 0 is less than or equal to x is less than or equal to 2. So I may have on the exam, and I might ask you, okay, so what's the start value of one of your periods? And here, our start value is 0. What is the end value of your period, one of your periods? In this case, because we did this, we can see it's 2. The halfway value between 0 and 2, you would sum that together and divide by 2 or multiply by a half. So 0 plus 2 is 2 times a half is 1. So halfway mark, and that's kind of easy to see. Halfway between 0 and 2 is 1. But it's not always so easy to see. So that's how you would do it. To find the quarter-way mark, we're looking at our start and halfway mark, summing those together and dividing by 2. So 0 plus 1 is 1, divided by 2 is 1/2. So our quarter-way mark is 1/2. To find our 3/4 mark, we would look at our halfway mark and our end mark and find the halfway point between those two. So summing those values, 1 plus 2, which is 3, and 3 divided by 2 gives us 3/2. Okay, so plotting those points, I have 0, 1/2, 1, 3/2, and 2. So I also noticed that I'm having some vertical shift in here. I have this -1. I also want to look at my amplitude, because that's going to affect things too. And my amplitude is the absolute value of the coefficient in front of the sine function or the cosine function. So the absolute value of -2 is +2. So what is the amplitude? it's 2. So normally my maximum on that graph of -2 sine pi x, that would be 2, and my minimum would be -2. But I'm shifting everything down 1 unit. So if I shift down my max of 2 1 unit, my max now is at 1. And if I shift my minimum down 1 unit, so -2 is my minimum minus 1, that's going to be -3. My midway line for the original function before I vertically shifted it was my x-axis. And so I'm shifting my midway line down 1, so it's at -1. So we're going to treat like this as like it was the x-axis when we graph this. So I notice I'm graphing a sine function. Sine function starts at the midway line. And so our start value was 0 at the midway line. I'd have this point here at 0, -1. Normally sine would increase, but I have this coefficient of a negative in front of my 2, and so that's a reflection across the midway line. And so at my halfway mark, I hit my minimum. At 1, I get back to my midway line. At 3/2, I hit my maximum of 1. And then at 2, I'm back down to the midway line. And so here is the graph of 1 period of that sine function. So our period, we want to look at the length of 1 period. Well, you have your start value and your end value of 1 period. So you want to find that length. If that was shifted to left or right, it wouldn't be as easy to see. So you would take your end value minus your start value. So 2 minus 0 in this case is 2. So my period is 2. My range are the y values that I'm using. And the y values I'm hitting on this graph is everything between going from smallest to largest, -3 to 3. And we're hitting those points, so we're going to include that in there. So a couple ways we can write that: interval notation, bracket -3. And I don't know if I just said 3, because if I did, that was wrong. It's -3 to 1. So -3 is less than or equal to y is less than or equal to 1 is another way to write that. And then we already did part D, graphing that. So you should be able to look at a graph and also be able to find the equation of the graph by looking at it. So looking at the following equation, we have secant theta is equal to -5/4. We're given that tangent theta is less than 0, and we're asked to find the remaining trigonometric functions. And so looking at this, we have to figure out first what quadrant theta is in. And so first of all, it says that tangent theta is less than 0. And so that tells me that tangent theta is less than 0. So it's either in quadrant 2 or quadrant 4. And so now let's look at the other trigonometric function, secant theta. It's negative. It's -5/4. So I think to myself that secant theta is 1 over cosine theta. So it's wherever cosine theta is negative, which is in the second and third quadrant. And so that overlaps with tangent theta is negative. Sine theta would have to be positive if cosine is negative. So that would have to be in the second quadrant. So we know that theta is in quadrant 2. So that's going to help us with what sine is our trigonometric function at that angle. So now we would create a triangle. And so creating a triangle, put theta in there, a right triangle. So secant theta, that is 1 over cosine theta. And so secant theta is hypotenuse over adjacent. So hypotenuse side would be 5, and my adjacent side would be 4. So now we need to figure out what the opposite side is. So using the Pythagorean theorem, the opposite side would be the square root of the hypotenuse squared minus the other side squared. So this gives me the square root of 25 minus 16. 25 minus 16 is 9. So the square root of 9, which gives me 3. So we know that this side right in here is 3. And so now we can get all the rest of our trigonometric functions. And so let's look at cosine theta. Cosine theta, that is adjacent, which is 4, over hypotenuse, which is 5. We could have gotten that from looking at 1 over cosine theta, which is secant theta. And it's negative in quadrant 2. So we get negative 4/5. So I didn't need the triangle there for this one, that one. Sine theta, we're in quadrant 2, so it's positive. And sine theta is opposite over hypotenuse. So this would be positive 3/5. Cosecant theta, that's 1 over sine theta. So the reciprocal of sine theta would give me back 5/3. And it's also positive in quadrant 2. Let's do tangent. Tangent theta is opposite over adjacent. In quadrant 2, and it told us this, it's negative. And so opposite over adjacent, it would be 3/4. So this would be negative 3/4. And cotangent theta, let's read this up. Reciprocal of tangent theta, so this is a negative 4/3. So given that information about one of our trigonometric functions, enough information to figure out what quadrant theta fell in, we could find the remaining trigonometric functions. Okay, so there was a question about how I knew that this was positive or negative, which trigonometric functions were positive or negative. And again, we had to kind of go back through what we were given to figure out where our angle had fallen. And looking at tangent theta, which is, if we thought about the point, it's y over x. And so tangent theta is less than 0 when one is positive and one is negative for our point. And so tangent is negative in that second quadrant and then the fourth quadrant. And then looking at secant theta, that's 1 over cosine. Cosine represents the x of the point on the unit circle. And so cosine is negative just in quadrant 2 and quadrant 3. And so we're looking at what both of those hold true. So that would have to be in quadrant 2. And then thinking about these in terms of x and y values, you can determine, is that trigonometric function positive or negative in those quadrants. So looking at the following, we're given a point negative 1/3 and 2√3/3. We're given that that's a point on the unit circle that corresponds to the value of t. Find the 6 trigonometric functions. So I would first graph this to figure out which quadrant t fell in. And so graphing this, I get my x value is negative 1/3. So I'm just gonna put that there. And my y value is 2√3/3. And this is not necessarily to scale. And so now I can create my triangle. Actually, let's put our point there first. And so now we can create our triangle. And so we're always forming our triangle, that right triangle, with the x-axis, which would give us an acute angle. So an angle between 0 and 90 degrees. And so right here, we have t. So I know that t is falling in quadrant 2. And so again, that's going to help me with, is my trigonometric function positive or negative in that quadrant? And so now I'm going to create my triangle. and figure out my missing side. And so I know that this length in here is my y value, which is 2 root 3 over 3. And I know that this value right here, that length is 1/3. And so I need to find the hypotenuse, and the hypotenuse is equal to the square root of 2 root 3 over 3 quantity squared plus 1/3 quantity squared. So squaring 2 root 3 over 3. So 2 squared is 4 times root 3 squared, which is 3, all over my denominator squared, which is 9, plus 1/3 quantity squared. So squaring the numerator, I get 1, and squaring the denominator, I get 9. I could reduce this, but I'm going to want to combine the fractions, and I already have a common denominator, so let's not do that. And we notice that 4 times 3 is 12. So I have 12 ninths plus 1 ninth is 13 ninths. So now using rules of radicals and fractions, I can take the square root of my numerator, which is 13, all over the square root of my denominator, which is 3. So we got this hypotenuse is square root of 13 over 3. And so now let's just use the relationship of sides and determine, is that trigonometric function positive or negative in that quadrant. And so sine of t, I know that sine, my y value, in that quadrant 2 is positive. And sine is opposite. So opposite side is 2 root 3 over 3 divided by the hypotenuse, which was root 13 over 3. So we have some stuff to clean up here. We have a fraction within a fraction. And so that's the same thing as the numerator, 2 root 3 over 3, times the reciprocal of the denominator. So flipping the denominator, we get 3 over root 13. So simplifying this, 3's cancel. I notice I have radical in the denominator, so rationalizing that denominator can multiply by a fancy one, square root of 13 over square root of 13. So this gives me 2 root 3 times root 13. So rules of radicals, same index, it's a square root, both of them. I can multiply underneath the radical. So square root of 3 times square root of 13, that's square root of 39. I have this 2 in front of the radical still. All over root 13 times root 13, which is 13. Okay, so sine of t, just put these down here after we simplified and rationalized the denominator, is 2 square root of 39 over 13. Cosine of t, I'm in the second quadrant, so cosine, which is the x value of the point on the unit circle, is negative. Oh. Okay, and then doing this, we get, I think I'm doing more work than I need to, cosine of t. So we get adjacent, which is 2 root 3 all over 3 over hypotenuse. I'm sorry, adjacent is not that. Adjacent is 1/3. All over the hypotenuse, root 13 all over 3. So flipping this up, we get cosine of t is equal to 1/3 times the reciprocal of the denominator, which is 3 over root 13. That's negative still. 3's cancel. We have negative 1 over root 13, rationalizing our denominator. multiplying by a fancy 1, square root of 13 over square root of 13, we get negative 3 root 13 all over 13.
Would we not cancel the 2 3s?
Oops, thank you. We did cancel the 2 3s right here. And so we don't have that 3. Thank you. Right there. Don't have that 3. Okay, so I just paused the video because I was concerned. Knowing the fact that when I'm on the unit circle, my cosine value is my x value and my sine value is my y value. So if that was the case, then I should have gotten that cosine of t was negative 1/3 and sine t was 2 root 3 over 3. And also I would know, and this should have came out if I had written this down right, on the unit circle, if I made a circle here, my radius, right? The radius on a unit circle is 1. And so not knowing or forgetting what I just said about this being cosine t and this one being sine t, when I have found the hypotenuse, this should have been 1. So I went back and I looked at my work and then I still got root 13 over 3 and I didn't get 1 for my hypotenuse. So I looked at the problem, back at the problem that it gave me, and I noticed that this right here should have been root 2. So technically, if this was a problem that didn't say that it was on the unit circle, it just said that P is a point. And then let's say that T is the angle to the line that joins that point to the origin, then we would be doing this correctly. As a point on the line. Oops. Where T corresponds to the line where T corresponds to the line between the point and the origin. Changing the problem to fit our needs of right over here. And so now we could just continue on. It would have been so much easier though if I had noticed that and I had given that as the right problem to do these, knowing that was X and our Y value. And maybe we could go back and do that after, but this was a 3. Okay, so cosine T was this, sine T, we need to find the other 2 or other 4. I know that secant T is 1 over cosine. So 1 over cosine, if I had looked at this before I rationalized the denominator, this would have given me negative, and taking the reciprocal, negative root 13 over 1. Cosecant T, looking at the sine T before we rationalize the denominator. And we were going to have to rationalize it anyways. because we had a radical both in the numerator and denominator. So let's just flip this. So cosecant t is equal to 13 all over 2 square roots of 39. If I multiply by root 39 over root 39, we get 13 root 39 all over 2 times 39. 13 goes into 39 3 times. 2 times 3 is 6. So this would be root 39 all over 6. Tangent t, that's opposite over adjacent. So that would be, and it's negative in quadrant 2. So it's 2 root 3 over 3 divided by 1/3. Flipping that 1/3 up, the 3's would cancel. So this would be negative 2 root 3. Cotangent of t, that's a reciprocal of tangent. So cotangent of t is 1 over, so negative 1 over 2 root 3, rationalizing the denominator. I get negative root 3 all over. Root 3 times root 3 is 3 times 2 is 6. So now looking at the following, we have the angle of elevation of the top of the building at the distance of 15 meters from its foot on a horizontal plane is found to be 60 degrees. Find the height of the building. Okay, so let's start putting a picture together of what it just said. So it says the angle of elevation to the top of the building at a distance of 50 meters from the foot of the horizontal plane. So it's telling me that I'm standing, and 50 meters over here, we have this building. And it's telling me that the angle of elevation, so looking at the horizontal, we're going up for elevation. If it said depression, we would go down. And so we're going up 60 degrees. And we want to find the height of this building. And so looking at this and my angle, with my angle, I want to find my opposite and I know my adjacent. So thinking of the trigonometric function that uses opposite and adjacent would be tangent. So I'm going to want to use tangent here. And so we have tangent of 60 degrees is equal to the opposite h all over the adjacent, which is 50 meters. Tangent of 60 degrees, you should know. That one is root 3. So root 3 is equal to h over 50. Multiply both sides by 50. So we have h is equal to 50 times square root of 3 meters. So if I asked this without a calculator, you would leave it like that, or you would put it in approximate form if I allowed a calculator. Okay, so the next one says from the top of a tower, 30 meters height, a man is observing the base of a tree at an angle of depression, measuring 30 degrees. Find the distance between the tree and the tower. Okay, so you have some tower. It says the man is on top of the building, and he observes a tree and an angle of depression. So when it says angle of depression or angle of elevation, you always start at the horizontal. You go up for elevation, down for depression. And so I'm going down 30 degrees. So we're going down 30 degrees. He notices the tree, the base of the tree. And we want to find this distance in here. So, and we're given that the top of the tower he's standing is 30 meters. So I'm giving this side as 30. So with my triangle, let's figure out what this inside angle of my triangle is. And so if the other piece was 30 degrees, and I know this piece here has to sum to 90 degrees, this would have to be 60 degrees. And so with my triangle from 60 degrees, I want the opposite and I know adjacent. So again, I'm going to use tangent because that deals with opposite and adjacent. So tangent of 60 degrees is equal to the opposite side, which is D, all over the adjacent side of that angle is 30 meters. So tangent of 60 degrees, that is the root 3. Equals D over 30. So D is equal to 30 times root 3 meters. Is the distance between the base of the building and the base of the tree. Okay, so looking at this, we have a balloon is connected to a meteorological station by a cable of length 200 meters inclined at 60-degree angle with the ground. Find the height of the balloon from the ground. Imagine that there's no slack in the cable. Okay, so we have some station. We have some balloon, and it's attached from the base with the ground. So we have this ground here, and it's inclined by 60-degree angle. So we have a 60-degree angle. And then we have some cable. And we know that cable has a length of 200 meters. And then we have our balloon. And we want to find the height of the balloon to the ground. So form our right triangle. From our angle that we know, we have the hypotenuse, we want the opposite. So thinking to yourself, what uses opposite and hypotenuse? Sine. So we can look at sine of our angle 60 degrees is equal to the opposite side, which is h, all over the hypotenuse, which is 200. Sine of 60 degrees, that's root 3 over 2, is equal to h over 200. So multiplying both sides by 200. So 200 times root 3 over 2 equals h. 2 goes into 200 100 times, so we get h is 100 root 3 meters.